So chapter one is basically review of a complex number. By the way, in basic engineering, do you cover complex number linear algebra? Yeah. You do? Okay, that's nice. Some of you already had the experience of this. So the whole definition of the complex numbers is because of this situation. So if you want to solve xi plus 1 equals 0, and the solution come up will be something called I. And what that I means is I square equals, if it's a 1, it doesn't make, it will be, everybody knows that's normal. But I square is what? Definition is that in -1. That's the definition of this. Yeah, this basically is the cornerstone of the complex number, and leads to many very interesting properties and observation. I have to say I'm trying to explain this to my daughter when she was in middle school. Quite an interesting way. It took me a long time trying to explain why we need this. So I actually watched many of the YouTube movie myself, try to explain my daughter why this is important. Yeah, sorry, I don't want to go down there. You are a graduate student, you should know this. So that's easy for me. So okay, so but and when I was a student, it also took me a long time. Why do we have to deal with? I never see this in my life. So why do? But apparently, if you go into the quantum world, and this actually even in some physics basic principle, this I is very convenient way trying to model things. The way I understand this, the complex number is just one kind of a modeling. We use modeling to describe the world. That can be a mathematical model. It actually doesn't have to be, it can be a logical model. It can be something we have made up in our mind, try to describe the world. I mean, there are many people made up many things to describe the world. I don't want to go to detail. Mathematical model is not the only way, but at least in science and engineering, mathematical models seem to be working. I mean, many of the mathematical models predict the real world, it describe the real world, and we develop engineering, it follows, right? Like a Newton's law. And that's just a mathematical equation. And we use a Newton law to build many things, right? Including the airplane, the cars, so whatever, the hammer, it works. Many things. The artillery, the guns. I mean, many things follows Newton's law. But then there are other things. For example, I remember there's a YouTube video describe the Schrödinger's equation with the I complex number. Without the I, is according to the video Schrödinger himself, he doesn't like to put I there, but it is necessary to use I to describe his idea. So my understanding of this complex number is it's a tool we use to describe the world. And apparently for the quantum information, quantum computing, that I is necessary. It's just a tool we have to use to describe the world. That's just my understanding. I mean, how you understand, many people understand things in different ways. That's just my way to understand the necessity and the usefulness of the I and the complex number. There are many, but given this, and then we can think about the I. Well, if I square equal, how about I this? what would then this be?
Be negative I.
Why is that?
It will be I squared times I.
Okay, so Joshua says, and so remember, this is still follow the same algebraic rule. So this will be I2 times I1. Well, we know I2 is -1. So this is -1 times, oops, sorry. My I and the 2 without the dot look exactly the same. I need to be careful of this. So, all right. So this will be negative I. Yeah. So this is following the same algebraic rule. Is there a way I can hide the I? So that's the I. And then, well, the complex number definition will be and sometimes we just call that a C. A plus BI, that would be a one complex number. So, well, if you think about this, so you have two complex number. Let's say C1 is -3 plus I. C2 is 2 minus 4I. And we can actually then just follow all the algebraic rules. So then we have a C1 plus C2 will be -1 minus 3I. Is that correct? Oh. Yeah. And then we can also have C1 times C2. Okay, how do we do the C1 times C2? Is communicated. So that's this one, C1 times C2. Okay, I'm going to let you work out. Okay, let's write it down. -3 plus I. 2 minus 4 plus I. So basically, I'm not sure distribute the word. So I'm going to use 2 times the first term and then minus 4I times first term, then add them up. So so that will be -3 plus I times 2. And then what? Plus actually, no, not plus, minus. Sorry, my bad. Yeah, that image is really annoying. Okay, so that this one have -6 plus 2I, and the other one I have 12I minus 4I squared. Is that correct? So these two, I have 14I. On this one, I have -1, so this become +4, is it? So this is -6 plus that plus that. So the result is -2 plus 14I. Okay, I hope I did algebra correctly. Is there any correction we shall make?
You and Mojave or Hanadi got the same answer.
Oh, Hanadi, wait, how do you know Hanadi got
In
it?
his chat.
In the chat. Oh, I see. Okay. All right. Thank you. Uh, all right. So basically, complex numbers still follow the algebraic rule we have learned. So in that sense, it's quite a relief. There's no special operation of the I follow. The algebraic rule still works. So that's quite a relief. There'll be other property also follow. That will be, let me see. Sometimes we also write it like this. So there's another convention. So C sometimes also write like this, A and B as a complex rule. So instead of A plus B, BI, sometimes we just use this, sorry, that's not very clear, comma, B as a complex number. So sometimes that's also a way to write that. You can see this parenthesis A comma B is actually very convenient, also concise. In fact, you can also understand the real number is one dimension, not I is another dimension. This A comma B is also, in my mind, intuitively make more sense. Yeah. So, and okay, so let me see what the other property we want to go over. The book actually have many exercise. For example, the book I have an exercise. There is a solution called question mark, and you can verify whether -1 plus I is the solution of this equation. Without the I there, it's hard to find a real number solution for that. So how about I'll give you 5 minutes to verify this. We could also put this as a Python exercise. So, right. So, how about this? Yeah, you can do that. Today's homework will be write a Python code, also verify that. So, yeah.
The plus and minus I
Say it again.
would be plus minus I. So -1 plus and minus I.
Yes, this is one of the solution. If you I guess yeah, solutions. But there's actually either, I guess this also can be x plus 1 squared equal -1, and then it becomes quite obvious. So so then we have x plus 1 equals plus minus I. So x. Sorry, I'm not verifying. I'm actually solving this -1 plus minus I. So, but you can verify that that is the case. So, are we okay with this solution? Oh, okay. I guess you can expand the planning, and I just reformatted. I wouldn't say rearrange, not reformat. We reformat the Word document, but mathematical formula, we rearrange the formula. So rearrange the formula and then just solve this directly. So, so okay. I think because this course is called quantum computing for computer science, if we have an exercise, I wouldn't require you to solve or prove anything mathematically. Probably just write a code to find the solution or verify it. Yeah, in fact, if you think about it, if you can mathematically prove, probably that's very simplified way. In many real world situations, computational solution probably the only viable one anyway. So, okay, that's so there's a lot of algebra of the complex number. Is actually very similar to the algebra rule we have learned from. So since like for example, if we have two complex number, so A1, so A1, B1, one complex number plus A2, B2. If we add that two complex number, it basically become A1 plus A2, B1 plus B2. The way I look at it, if I look at the part before the comma is one dimension, the part after the comma is another dimension. It's basically two kind of independent dimension. They both are additive. So, and there'll be multiplication, we can just expand them. It's yeah, it's multiplication of not two dimension. That's a bit hard to imagine. But if we think about it in a geometric way, that's actually is the surface. Yeah. There will be geometric interpretation of complex number and complex vector in the next chapter. So. In fact, for quantum computing, there's a whole many of the theory are built on that geometric interpretation. So it's a yeah okay. So this is something called the general rules of algebra. Let me summarize here. Commutative. Commutative basically means C1 plus C2 equal to C2 plus C1. Another one is called associative. In this case, basically C1 plus C2 plus C3 becomes C1 plus C2, oops, sorry, plus C3. And they are also distributive, distributive. In this case will be C1 times my smooth process and C looks really similar. I need to figure out a way to distinguish them. Sorry, my handwriting not very good for quantum information either. I'm going to write my process like this. Okay, C2.
It's difficult on a pad as well.
Sorry, what?
It's difficult on an electronic pad as well.
maybe, yeah, so, yeah, so, okay, let's make it. Okay, let's look different now, okay. So, distributed that we see, that's correct. It should be, yeah, just spread them out times C2 plus C1 times C3. Okay, let me see what the other rules. Okay, so there's another important concept called modulus. Of complex number. This, my understanding, this is basically treating complex number like a Euclidean geometry. So the modulus definition will be for a complex number, if we take the modulus, its definition will be the complex number of A plus BI. That's the definition of a modulus. If you think about the if we in the Euclidean space, if we have the A and B, that's A, that's B. What that modulus does is basically that's B, that's A, and we take that as a modulus. Sorry, that's probably too small. Yeah. That's basically the modulus. Yeah. And later on, when we see actually, there's actually another way to interpret this. So another way to write the modulus will be if we just use the square, that the modulus of the complex number is the sum of the square of the A and B. So okay, so there's another definition called a conjugate. Conjugate complex number. And in this case, we have so if a complex number C equals A plus BI, and then we have the conjugate, which is A minus BI. And so the question now, if we have C times C conjugate, what do we get?
If the real component is C, then just A squared.
Okay, let's verify that. So we have A plus BI times A minus BI. A squared plus ABI minus ABI minus B squared I squared. So I miss a dot. This will be minus 1. So
minus
plus BI. And these two canceled out. So we have what? Oh, sorry. So what is this?
the magnitude squared.
Yeah, this is basically is a modulus. Sorry, what?
It's the modulus and modulus squared.
Oh, modulus square. Sorry, thank you. Yeah, modulus square. Yeah, modulus square. Sorry. Yeah, so that's the modulus square. Right? That's modulus square. Thank you. Yeah. Okay, so there's some other definition. I'm going to just skip it. Yeah. So okay, so the geometric of complex number. This is very important part. So geometry of complex numbers. So in this case, we basically have the axis. One is this is the real part. The other one we call that imaginary part. And then this will be the so-called complex plane, the geometry. And then we will have the modulus, actually. The modulus, as we say, is just the length of that two. So in this case, so did I write it wrong? I flipped the A and B, sorry. The A should be, my bad. A should be the horizontal one, B is the vertical. I flipped that, sorry, I apologize. Let me just erase it. That's nice part of electronic. Erase it completely. But the bad part is I'm recording it as well. So, okay, yeah. Okay, the real part is the A, sorry. This is the A, and the vertical part is the B, sorry. So I'm going to use the different color, blue, is that blue? Yeah. So let's say the A is here. That's the A. Vertical one, the B is there. Or maybe now that I can use colorless, the B is green, the A is blue. Okay. No, whoops, just have to be, sorry. Okay, so now we have the A and B. How do we find the modulus? The modulus will be, oh, yellow and white is terrible. I'm going to use the blue again for the A. Yeah, excellent. I was trying to illustrate it using the geometric terms. So that's the B, this is the B, and this will be the A. and a square, b square will got. Sorry, I drew a bit off the diagonal. So that's the modulus. C. Yeah, this is a very nice geometrical interpretation of complex number and the modulus. Yeah, the things about math is it's self-logical, coherent. It's very nice. So even though we added that I, but all the mathematical algebra, geometry, they still stand. This is very, I guess, it doesn't have to be if you really think about it, but it is self-consistent. So now here's another way to look at this. It's called, I'm trying to say on the definition. Here's another way to look at it. This now that we have this one, we can call this of the phase. Now you might remember in algebra there's a geometric interpretation. You can convert x and y coordinate into a polar coordinate. We can do the same thing here. This is especially the case when we have a real axis, imaginary axis, but what happened in the between? So that will be a combination of the two. And then in this case, that will be the phase angle. See that? That will be the phase. This is really thick. And the other one will be magnitude. So that modulus will be the magnitude. And this is actually the important part in the Schrodinger equation, where the phase angle with I is actually turns. Now with that, there is actually another definition. I'm trying to see the. With that, the definition will be. Sorry, I didn't write this one down. I'm trying to find this. Yeah, the complex number now will become, so it was, the complex number was, the definition was A and B with the real and the imaginary. Now it can be wrote as the magnitude and theta, which is the phase. So this is actually, I found actually this magnitude and phase is more intuitive, especially when giving all those the quantum state. I found this one is actually more intuitive than the A comma B. Yeah. So that means from A and B to rho and theta, there's a conversion using the modulus. But how is A and B related to rho and theta then?
And A essentially is rho and theta is the I, right?
No.
Rho is the root of A squared plus B squared, and theta is arctangent B over A.
That's correct. But how do we write down A equal to rho and theta?
Where A is rho times cosine of theta, and then B is rho times sine of theta.
Yeah. So let me. Very good. So that is basically rho. So A will be rho times cosine of the rho. B is this one is what's the term of that? I forgot the in geometry. What's the term of this side? Hypotenuse. I forgot. Sorry. Say it again. Hypotenuse. Yeah, rho times sine theta is B. Rho times cosine theta is A. So yeah. So then we have the basically that. So and then it comes the most surprising this will then become a definition. Yeah. This is it has always puzzled me when I was a student, but this is really amazing mathematically. That apparently that is essentially the same with the Euler exponential form. Yeah, this with that form, many of the mathematical theory will be much more easier. If we directly use the top form, sometimes it's very hard. But once we use the exponential, many of the things can be done much easier. Yeah. So yeah, so this is whoops, yellow. Well, that is terrible. Yeah. Let me write a C here. This is a very amazing complex number mathematically. Yeah. So and the amazing part of this exponential is follow the same algebraic rule again, which means if E I theta times I theta plus, they all follow the same thing. Yeah. So and sorry, I forgot, when does this class end?
1:30.
Okay, then let me see what other content I need to go over. I think I've covered the most important part. I think of course, there's a property of this exponential form we can't go over.
That last one uniquely identifies a point in space.
It's basically exactly the same thing. Yes, yeah. It is amazing, isn't it? Yeah. So using one form. So
That's one use.
oh, sorry, what?
That's one use for it.
Yeah. So, but let's do this exercise. Let's do this exercise. I'm trying to see interesting exercise. Okay, this is an interesting exercise. It is confusing to begin with, but once you get the hang of it, you'll realize it actually makes sense. For example, I have a E I theta 1 times theta 2. How do we expand this?
Write that as product of e to the I theta 1 times e to the I theta 2.
Okay, so the question is why we can't write it out.
Because the magnitude is 1, so rho is 1 for both of those complex numbers.
So this will become yeah, but why it makes sense in the geometric sense? Remember this one is actually this one. Let's just use the cosine. This is cosine theta 1 plus I sine theta 1, right? Oh, sorry. That's the no, actually that's the this will be cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So apparently, if we expand this, follow the trigonometry rules, it actually goes back to the same result. The book does have the proof of that.
Cosine A plus B is 1/2 cosine A times cosine.
Well, no, that's not how the book proves it. I'm going to leave the proof to your own reading because I need to also remember the trigonometry formula that how that too
Proof is in the book.
is in the book. Yeah, it's in the book. But you can actually go the proof to show why it makes sense. But even though you can ignore the idea is the exponential actually the result is the same if you go back to the trigonometry. So the exponential form indeed reproduce the even though I don't actually really know, I forgot the trigonometry formula myself. But the exponential is much easier. You don't have to remember this. That's the point. Yeah. So without going through all the trigonometry proof, using exponential is much easier to do it. That's the point, right? If we don't use this form, use the trigonometry form, it's just much more cumbersome. It's also not very intuitive. Yeah, even though the result will be exactly the same. Yeah, that's the point of it. So, yeah. Okay. Oh, gee. To be honestly, this we have covered a lot the entire chapter. So, okay. As a whole, I guess you can reading also try to run a Python code to reproduce some of the result. Yeah, so, you don't even have to tell me. I'm trusting you will probably dying to write some Python code. Yeah.
Use something like PySim or something like that.
I'm not sure. I think Qiskit should be have enough. Although, let me see. I think actually try to use IBM quantum learning. Maybe that's easy. But oh, I see. Sorry, I forgot their chat. Oh, some people put that in the chat. Okay, sorry. Oh, Hanadi, are you still there? Hello. Oh, sorry. Maybe she's also in class. Sorry. Okay. Sorry. My apology. I didn't see you put in the chat. Oh, that's
That's
interesting.
right. I'm here. Yes, I'm here. You just muted.
I was busy on my.
That's fine. Yeah, I understand that.
Okay. All right. I'll see you next time. Yeah. So, actually, next week I'll be traveling. So I mean, you can still come in here, but I probably will join on Zoom anyway. So, unless then you want to sit, you can kind of podium turn on the screen, then everybody can look at yeah. But it's funny if you also want to join remotely as well.
I think I'm gonna do that one.
Sure, yeah. It's actually more convenient. But with your class, sometimes it works. For graduate student, it works, but for first year students, sometimes I don't know. Sometimes they feel if someone stand behind, they are more confident of doing things. Maybe it's just like the kids are playing, but they always ask the parent, "Wow, can look at me?" Something like that. Sorry, I'm a bit talking far away about it. Yeah. Sorry. That's,
I wanted to mention one thing, Professor.
oh yes, Hanadi. Yeah.
The required book is actually not mentioned in this syllabus. I bought it like immediately when I saw it because I thought that is a second. So I just wanted to bring your attention to that because I bought it through Amazon. I'm going to return it anyway, but I just wanted to bring your attention that the required book is saying quantum computation and quantum information. It says required on that one. And the one that is actually that you showed it today on the syllabus is a recommended one. So I just want to bring your attention to this one.
Okay, sorry. I wasn't sure when people submit this to bookstore, there's a different book.
I just wanted to bring your attention to that
Yeah,
to fix it for the future anyway.
Okay. Sorry. That must be a miscommunication with the bookstore. My apologies.
Maybe, yeah. I'll fix that on my side. I'm just gonna bring the other one, but yeah.
My apologies. Yeah, so
That's fine.
I would when I look at Amazon, there are so many quantum computing books. It's really
That's true.
yeah. I guess pick one, any book will work. So
it will work. You mean like it's fine?
Sorry, what? Oh,
you mean it's fine to keep that one, the one that says required?
I mean, you can return it if you can. I mean, if you buy the book with your own money, I mean.
Yeah, I bought it actually. I thought like this is better to have it as early as possible.
Yes.
But yeah.
I also bought 4 or 5 books. I decided it's probably not a good idea to ask all the students, say we have 4 or 5 recommended.
Yeah, that's true.
Right, yeah. So, yeah. Okay, my apology for that. Yeah,
that's fine. I just wanted to bring that to be fixed in the future, maybe, or something.
I see. It's probably too late to tell the bookstore we have made a mistake.
Yeah, that's true.
Yeah. Okay, I'll see you next time then. Yeah. So
all right, see you. Thank you so much.
Sure. Make sure you can have an account on IBM Quantum Experience.
Is it recommended to use our school account email? I mean,
it doesn't matter. I actually use my Gmail account.
Okay.
Yeah, I mean it's a free one. We don't want to use a paid one.
All right.
Yeah, I'm not sure how expensive it is to pay actually run an account. Not in at least not in that stage yet. So yeah. Okay.
Right.
Thanks for joining us.
Thank you. Bye-bye.
I need to fix all the fun things. This is so small.
I'm gonna talk to the guys. Hopefully I'll have a big.
Yeah, this was cannot be read.
You just gotta get better glasses.
Yeah, this is
They're right across the way there.
Yeah, the IT, going there something.
At least they use something.
Yeah.
If this is exam, I'm going to say you should cover it. I don't know. I think that they wanted to put it out there.
So that was when I did my thesis, so I got the equations that I used, so.
This guy,
It's a pretty complex.
you need the
technique set.
Fourier transformation.
Yeah, so that's the magnitude, that's the Fourier transform, and then that's the complex to fully represent.
That is.
Yeah, he has the exponential
Seven,
function.
at the final.
Well, you know, if you do this, actually, the next person actually.
Yeah, it's so I came to the exam in a tank top.
Right, yes. Okay, well, this is impressive.
So, I mean, I guess that's kind of my,
Yeah.
that's my cheat sheet, I guess, but.
For the next person, for the person sitting on your left.
So
So,
I've actually ended up using it, I was doing some math on the board.
Nice. Oh, you,
Yeah.
I guess you can look at, you know, yeah.
So no upward index.
That's true, you have to look at the
Mhm.
upside down view.
Yeah, but I've been doing complex math, you have to use it for digital signal processing. And then AI, you can do all those transforms and then internally some complex math. It's up to us.
Okay, maybe